Okay, let's get started. So this recitation, I'll be talking about optimization methods. We'll do a quick overview of kind of the basic optimization forms that you should probably know. There's a lot to optimization. There's a whole class on it that's, a great class that you should take if you're interested in this kind of stuff, 725. And there's obviously a lot more than is covered in that class too. So we'll just be doing some of the stuff you should probably know for the purposes of this class. So why do we care about optimization? Well, when we're doing machine learning or statistics, a big part of what we do is we have a bunch of data, we come up with some possible forms of models that we might use for that data that we can then use those models to do classification, regression, clustering, whatever kind of actual problem we want to solve. So for example, we might want to find the best discriminative line, which is the kind of thing that the perceptron does. We might want to find the best generative model, which is where, like in naive Bayes or a method like that, we assume a probability distribution generated the data, and then we do things based on those assumed distributions. And in that case, we want to find the best matching model, so things like maximum likelihood estimation, maximum a priori, even method of moments, other ways of fitting probability distributions, we can all express as optimization problems. So Jeff mentioned in class yesterday that a lot of times we'll be doing empirical risk minimization, which takes this form, where we have a bunch of data X, and we want to find the model that minimizes some loss function for each data point for the given model, plus an overall penalty on the model. So this might be something like, in a map case, the penalty on the model would be the prior on what the model should look like, and then the loss function would be something like the probability density under that model of that data point. So this would be minimizing the negative log probability density of the data under the model if we do this as a map. But as we mentioned in class, this loss function can be something more arbitrary than that too, something that doesn't necessarily have a probabilistic interpretation. Okay, and so the way we do this minimization is optimization, which makes sense. Optimization means, minimization or maximization. They're the same thing. You just negate the thing you're minimizing and then you're maximizing. So when we can, we like to do convex minimization or concave maximization. They're the same thing. And the reason we like that is, well, there's a couple of reasons. One is the nice property that convex functions have basically no local minima. So you can't get trapped somewhere that looks good. Everything near it is worse, but there's somewhere else in the space that would be a better solution. That's really hard to deal with. So when we can, we want to avoid that kind of thing. So it's nice to do convex minimizations when we can, and when we're coming up with models, if we can tweak our model in a way to make it convex, that's great. It'll make it a lot easier to deal with. But sometimes our model just isn't convex, and then we'll have to deal with optimizing it in some other way. So a big example of where that happens is in neural networks, which we haven't talked about in class yet, but you've probably mostly heard of. When you're training a neural network, if it has more than one layer, the objective function isn't convex, and that causes a lot of problems in terms of optimizing it. For probably 15, 20 years, people gave up on neural networks because they just couldn't figure out how to optimize them. Okay, so in some way, sometimes the best thing we can do for optimization is if we can just think about it and write down what the optimum is. So you guys did this problem on homework 1, ridge regression, where you take that loss function, which we said we could interpret as a map model for the data. So this is the loss function that we have. The difference between our linear predictions and the true values. plus a penalty on the size of the betas, which is equivalent to a Gaussian prior. So you guys in homework 1 basically took the derivative of this with respect to beta. And so that you found was, basically that. If you set that to 0, then you get the solution sorry. Did I do that right? No, I didn't. Yes, there is an x in there, thank you. I think it's on that side, right? So, yeah, okay, so I did that wrong. But the point is, there is a form which basically looks like that. Involves that term, multiply it by x, right? So this is the main part of the answer. And then you multiply it by y or something. I should have written that down, sorry. But so we know that is the minimum of that loss function. And no matter what beta we choose, that's the best beta. And if we can actually compute, if we take our data matrix, do all that stuff, invert it, then you end up with the answer. And you don't have to do any kind of gradient descent type thing, an iterative solution. So that's great if you can afford to do that kind of inversion. But if you have a really big X, inverting matrices is really expensive. So that's not always the best thing to do. And moreover, it's not always possible. You can't always analytically write down the gradient, find where it's equal to 0. So the simplest thing you can do when you can't write down an analytic solution like that is to do gradient descent. So that's basically, you just pick some starting point. A lot of times you pick 0, or you pick some random vector, or you pick something that you have a hunch might be close to the answer. And then you just kind of iteratively compute the gradient of the function you're optimizing at that point and take a step in that direction. So you're following the gradient down the curve of the function to the minimum. And this will only stop when the gradient is exactly. So if we could do this exactly, this would stop when the gradient here is 0, and then you just set x to x. Otherwise, you're always going to be moving. The problem is when we're doing this on actual computers, we don't have perfect precision arithmetic, and we don't have unlimited amounts of time. So we stop when we think we're close enough. And I'll talk about that a little more in a minute. So it kind of makes sense that you might want to, so the gradient locally is the direction, the negative gradient locally is the direction where the function is decreasing the fastest, right? So it makes sense that you might want to go in that direction. A way that you can think about it, a way that you can think about gradient descent, maybe a little more, just a different way of deriving the gradient descent rule, is you can take the function, and then using the gradient, you can get a linear approximation right there, right? So if we're optimizing, it's like basically x squared kind of thing, and we're right here, then we take a linear approximation that's like that. And because the function is convex, we know that this linear approximation underestimates the function everywhere, right? And so what we can think of gradient descent as doing is actually taking a quadratic that's tangent to the function right here at the point where you are, at x, and has some fixed curvature, eta. So there's the quadratic that is kind of a local approximation of what our function might look like. And what we do with gradient descent is then we take the minimum of that quadratic. Sorry for this terrible diagram. So we take the minimum of that quadratic and say that's the next point we want to do. And so we make that our new x. The true value is there, and we repeat. So that's just a little, and the curvature of that quadratic is what determines the step size that we're going to do. So that way of thinking about it will be useful when we're talking about other methods than gradient descent. We can analogize. Okay, so there are kind of a few things in this algorithm that, yeah?
You always use the quadratic no matter what the auto-determinable is?
Right, so if you're actually, so this is kind of, for any function you do that, that's what gradient descent assumes. If you're making it depend on the function, then you're doing a different algorithm. If you use, we'll see in a little bit that if you use the Hessian, the second derivative, then you're doing Newton's method. So that's why I said this, so that later we can see that actually adapting to the function's second derivative there gives you Newton's method. And then there are kind of things in between that you can also do. Okay, so one of the things we need to choose a few things when we're doing gradient descent. We need to choose the step size, we need to choose the termination conditions, and we need to choose an initial point. There's not really a lot of guidance on how you choose an initial point. Like I said, you can either start at 0, you can start at your best guess based on some simpler way of thinking where you think it might be big, or you can just start at some random point. So one thing that you can do is if you happen to be solving a problem where you have a solution to a similar problem, and then you're kind of adding terms on, you can start at the solution to the old problem, and that's called warm starting. So you start kind of near the minimum, and that'll help speed up your algorithm. So that's a useful technique in a lot of cases. Okay, so the other big thing we need to do is choose the step size. So here's a stupid example of minimizing a quadratic, like just x squared plus y squared in 2 dimensionals. So in this case, this is a pretty reasonable step size for gradient descent. It just goes straight in, takes, it doesn't take very long to get pretty close to the minimum, which is that magenta point there. So we started here, and then we took the gradient is pointing in. Can you see the cursor? Maybe. Okay, so we randomly started up there. Gradient points straight towards the center. We take a step. I think it's 0.2 of the way along the gradient. Keep doing that. We keep going towards the center. Stupid case. But even in this stupid case, if you choose the wrong step size, say you choose too big a step size, what it does here is we start up there. We follow the gradient. I think it's 0.8 in this case. And we jump all the way over there. We way overshot the minimum. And then now the gradient points the other direction, so we shoot back, and it oscillates back and forth, and it's going to take a long time to get into the center. Also, if we choose too small a step size, it doesn't oscillate, but it just is going to take forever to get there because we're being very conservative with how far we're going each time. So how can we choose the step size? Well, if you know something about your function, there are various things you can do. Like if you know the Lipschitz constant of the function, which is a bound on how fast the function can vary, then you can theoretically choose a step size based on that. That's the optimal step size. But usually we don't know that. So one thing we can do that's pretty simple and works pretty well in practice is called backtracking. So here, basically what we do is we start with a step size of 1 at each iteration. And so we just move entirely like a full step along the gradient. And then we check, okay, my function value at the new point, because that's the update rule for gradient descent, right? X minus eta times the step size, times the gradient. So we check if my function value decreased enough at the new one. If the function value at the new point is bigger than the old function value minus the step size, half the step size times the squared norm of the gradient. There's a theoretical reason why that makes sense. I don't know that there's a good intuition for why you do that value in particular, but the basic idea is that if the gradient is big, you're going to want to be able to decrease your function value more because their function's really steep there. So basically, if your function value at the new step is too big, you don't take that step. Instead, you take a smaller step, beta times the previous step size, and you try again. So this is basically doing a geometric backoff. So you try step size 1, step size beta, beta squared, beta cubed, so on, until you get a function that improves, that seems reasonable, like it improved the function value enough, until you get a step size that improves the function value enough. And then you take that step and you start over again with a step size of 1. So this particular algorithm for backtracking has convergence properties that are basically just as good as gradient descent with the optimal step size. You lose a small constant factor in your, small like multiplicative constant factor in your convergence rate. And in practice, it is a really nice default to use. Sometimes people do things like they keep the step size between different iterations, and then if it worked, they grow it, they shrink it if it didn't work. I don't know of a formal proof that works better, but in practice, sometimes it does. Okay, so the other remaining kind of variable in gradient descent is how you choose when to stop. So one thing you can do is if you didn't move very far, if the x at the previous step and the x at the new step are close enough for some arbitrary threshold that's close enough. Another thing to do is when the gradient gets really small, basically the assumption then is that if the gradient is really small, because the second derivative has to be positive, you have to be pretty close to the actual minimum, hopefully. Another thing is when the change in function value is small. So if you don't care so much about the actual value of the thing you're optimizing, the parameters, but you care that the parameters are almost as good as the best one. Basically, you don't care how far your parameters are from the best parameters, you just care that the parameters are almost as good. So where those would be different would be a case if you're optimizing a function like this. You can imagine that along this, if you're over here somewhere, then your steps might be changing x a fair amount, but they're not changing f of x very much at all. Also, this is similarly, the gradient will be small there. So when the gradient is small and when change in function value is small are very similar conditions. Another thing you can do is when you're backtracking and you keep, basically none of your step sizes are good enough, you just keep going smaller and smaller and smaller, then that's another reason to stop. Another way to stop might be just say, oh, I'm going to go for 1,000 steps, and then that's it. And you might do some combination of these. Okay. So another thing than gradient descent, a very similar thing that you can do, is called stochastic gradient descent, or SGD. So descent is in quotes there because it's not actually a descent method.
With that other one, would you ever want to go past the minimum, and then that's how you know you might be far?
So you mean like if you're here and then you're here? Yeah, so if the gradient changed signs. The problem, that might be a reasonable thing to do. The problem is that if you're in a different function and you went like that, then you might think you're done when actually you're still pretty far. So you probably have to combine it with something else to make that make sense. But it seems like a reasonable thing to think about. Okay, so for SGD, the motivation for SGD is that when we're doing gradient descent in machine learning, Usually what we're doing is we're minimizing, for example, in this empirical risk minimization framework, we're minimizing what's called the empirical loss, the mean of our loss function over the training set. And then we're updating based on the gradient of that, which is the gradient, the sum of the gradients at each point. So the reason we do that, really, is that we're trying to minimize the expected loss under under the generative model for this, under the actual distribution that generated this data. So we don't particularly care about the training set usually. We just use the training set because it's a sample from the underlying distribution of the data. So this mean over the training set, we think approximates pretty well the expected value over the whole generating distribution of our data. But we can also approximate that in other ways. For example, if we just take any one arbitrary, well, random, I guess random, not arbitrary, point from our training set, and we look at the loss on that, that is an unbiased estimate of the mean loss over your data set. Basically, if you take a single point that has the same mean as the mean of the distribution. And so what we can do then is do gradient descent, but instead of calculating the full gradient over the whole training set, we just calculate the gradient at a single point. So this gradient, this is the gradient term that we're doing in regular gradient descent over the full training set, which we usually call batch mode gradient descent. This is what we really want. This is just another cheaper approximation of this. So they have the same expectation and stuff. So SGD then is what's called an online optimization, because if instead of having, here's a training set that you downloaded from the Autolab server, you have a bunch of samples coming in some kind of streaming scenario, or like if you have like a web scale data set, maybe you have the data stored all over the place in different servers, and they can each send it to you, but you don't have to remember all of the old data. You can just walk over all of your data once, and if you have enough data, then hopefully after you've walked over everything, you've gotten close enough to the minimum. And if you don't have insane amounts of data, you just have a fair amount of data, you can repeat that process of walking over the whole data set until it basically, until some of the termination conditions that we saw before happened, or something similar. So the advantage of this is that you don't have to look at the whole data set on each iteration. You only have to look at one data point and calculate the gradient for one data point. So that makes it a lot cheaper to do a single gradient update. The downside is that your gradient, the steps you're taking get much noisier. So it'll take more iterations in the end to get to a good minimum, but of course the iterations are each so much cheaper that a lot of times it balances out. So one problem though is that, as I mentioned, it's not actually a descent method. If you're doing gradient descent, and you take you plot the function values over time, normally it'll look, something kind of like that. It'll be decreasing, not necessarily I guess strictly decreasing if you're doing backtracking or something. So yeah, this is true. If you're doing backtracking, you're only ever going to take a step if it improves by something. So it'll be strictly decreasing over time. With SGD, that's not necessarily true. It might look something like that. It'll go up once in a while. So that makes it harder to know when to stop, because a lot of the termination conditions are based on this not changing very much. But if it's increasing versus not changing, sometimes it's hard to tell whether you've actually reached a minimum or not. Okay, so I want to do an example of SGD. So let's talk about, or let's think of a linear classifier where our output, so we want to find Oh, that's why this is dark. Sorry about that. So we want to find a W such that for any arbitrary data point, the inner product of our weight vector W with that data point is about equal to the label. So that's the standard linear classifier setup. So you can do that with various things we talked about in class. I'm going to choose a loss function called hinge loss, which is basically the loss function is it's 0 if you got it right, and it's the amount that you got it wrong by if you got it wrong. So in a formula that looks like this. So basically, yi here is going to be either 1 or -1. So if yi is 1 and your predicted classification, w.x, is positive, then this number will be positive, that's negative, and so you get a negative number here, max of 0, and a negative number is 0. So if you got and the same thing if yi is negative and w.x is negative. So if you got the classification right, the loss is 0. If you got the classification wrong, your loss is basically w.x. I drew it wrong. The loss should be positive if it's bad. Sorry. The formula is right. Thanks. Okay, so that's our loss function. Now we're going to do SGD on that. So how do we do SGD? Well, you take this loss function and you take the gradient of it with respect to the model, which in this case is W. So the gradient of L is basically, if you're over here in the 0 part, then the gradient is 0. And so that's true when negative yi w.x is less than 0. And if you're in this part, positive part, then the gradient of this with respect to w is just negative yi xi. Okay, so our update rule then is xi gets xi plus our step size times the negative gradient, which is 0 if, okay, so this being negative means that yi is not equal to the sign, the predicted class. And if it is, then the negative of this is yi xi. Oh, sorry, if it's equal to the sign. So if you got it right, you don't do anything. If you got it wrong, you move eta times xi if it's positive. So if it's positive, or sorry, this is bad, wi. Okay. Then you move, you basically add xi to your weights. If it's positive, you subtract it if it's negative, times eta. So this should look familiar. Does anyone recognize something we did in class that is almost exactly this? Right. It's the perceptron learning rule. So perceptron is SGD with this loss function where you fix eta to be 1. So that's not, I don't think that's how Rosenblatt actually originally came up with it in 1958, but that's a way that you can think about the perceptron as doing SGD with this loss function. So some of the problems that the perceptron had, things like it doesn't actually converge if there is no perfect answer, that kind of thing can apply to SGD also, depending on exactly what the situation is. Okay, so we can also do, remember the point of SGD was just that we were doing something that approximated this expected loss, or the expected gradient of the loss. Oh, yeah.
Just one question. So, if the signs of yi and wt xi are same, so does the stochastic gradient descent just stop there? Because it could still be away from.
Right, so that depends on your, that's an example of when the termination conditions that I talked about for gradient descent don't make sense for SGD. Because if you did a thing like if your iterate doesn't change enough, which in this case means if your new W and your old W are close enough, then you don't move. Well, in this case, if you used that exact rule with SGD, then you would stop the first time you got one right, which is obviously too soon to stop. So yeah, good point. So with SGD, a lot of times, one thing you can do actually is you can split up your training set into a training set and a validation set. So then when you're optimizing, one thing you can do is look at the error on the validation set. And that should go down, not necessarily exactly monotonically, but hopefully close to monotonically over time. So that's a pretty good stopping rule to use for SGD. Okay, so the point of SGD was that we're approximating this expected loss just using a cheaper estimate. So we came up with an estimate, just a random point, which has the same mean, but a very high variance statistically because it's a random point. So one way we can keep the same mean, decrease the variance without increasing the cost of the iterations too much is to do what's called mini batch gradient. So that's when you calculate the gradient over not a single point and not the whole training set, but a subset of the training set, which we call a mini batch. So the idea there is that it's a little less variable than SGD, but it's still cheaper than full gradient descent. So it's helpful in that when you're early on in the optimization, you're not wasting a lot of time calculating over the gradient over the whole training set. But it's a little less wiggly and random and subject to noise than SGD is. So basically, it's kind of a happy medium in a lot of cases between SGD and full gradient, depending on what batch size you choose. I'm not aware of a lot of theory on what mini batch size to choose and stuff. There probably is some out there. But what you do in practice is you kind of choose a number maybe on the order of tens to hundreds that is a pretty small fraction of your overall training set size, but is still big enough to avoid so that you probably get a good sample from the overall thing. And in both SGD and mini batch, by the way, when you're actually implementing this, it's important to make sure that you're choosing random points or you're iterating over the points in a random order. So a lot of times, if you just implement SGD by walking over the points in order, then a lot of times you'll get a data set, for example, the data sets that we've given you for the homework problem so far, I think. A lot of times they'll have all the positives first and then all the negatives. So it won't train very well if you train it on all the positives first and then all the negatives. You want kind of a random mixing. So just shuffling your training set, for example, would accomplish that. Okay, so gradient descent, SGD, mini batch, all only work if the function you're optimizing is differentiable. Sometimes we want to optimize functions that are convex but not differentiable. So for example, this function here, the blue function, has kind of a bunch of sharp turns in it. So this particular function is kind of a silly arbitrary function, but there are a lot of things we do want in practice that have these kind of points where it's continuous, but the gradient is not continuous. So in that case, we can do subgradient descent, so a subgradient for of a convex function is any tangent line that that lies under the function everywhere. So remember that in a convex function, in a convex differentiable function, and this is one thing that we did that you show on homework 2, is that if you take a tangent plane anywhere along the function, it lies under the convex function. The tangent plane lies under the convex function everywhere on the whole space. So for subgradients, it's the same thing. It's any tangent plane that lies under the function anywhere. In a differentiable function, there's only one such tangent plane. If you move it up in any other direction, it'll cross over, basically, because that's kind of the definition of what a derivative is. There's only one tangent plane. For these subgradients, if you have a non-differentiable point, for example, the absolute value function, here's a tangent plane, there's a tangent plane, there's a tangent plane. There's a lot of them that are possible planes. Here's two red ones here. And so for subgradient descent, what you do is you do gradient descent, but if you're at a point where you don't have the actual derivative, or there is no derivative, you just take any subgradient arbitrarily. So like, if you're at a point where it is differentiable, you have to use the gradient because that's the only subgradient. If you're at a point that is not differentiable, you choose any one of them and just follow that, take a step along that. So that's nice that we don't really have to change the algorithm, and sometimes we can come up with these subgradients pretty simply. But the problem is that it becomes super slow. The bounds on subgradient descent are much, much worse than the bounds on gradient descent. Okay, so in a lot of cases, what we want to do is minimize. We have a function that has a couple of these points that aren't continuously differentiable, or that aren't differentiable, I guess. But our function can often be written as the sum of a smooth part, or a differentiable part, g, and a convex but not differentiable part, h. So one example of that, which is on homework 2, is the lasso. So the lasso, you can write the objective function as the standard linear regression thing plus lambda times the 1 norm of beta. And the 1 norm is just the sum of the absolute values of the vector. So this is like the absolute value function. In one dimension, it's the same thing as the absolute value function. So at this point, at 0, it's not differentiable. And then in more than one dimension, it's the same thing, just kind of project. If you take a slice of it along any dimension, it's the same thing. So in 2 dimensions, it's hard to draw because I'm bad at drawing, but it's like that. It's still sharp. There's a sharp non-differentiable point at 0, and anywhere else it is differentiable. So for this, it turns out that for the 1 norm, the only point where, so the subgradient is usually just really easy to find. It's just 1 in whatever direction. And then at 0, there's basically a lot of possible subgradients. But so for lasso, this part is a nice differentiable convex function. And this is the only nasty part. So it turns out that you can do something that's called generalized gradient or proximal gradient that takes advantage of the differentiability of the smooth part by doing this, using this thing called a prox function. So you don't have to know the details of this. We're not covering it in lecture, but it's nice to know that basically what you do for proximal gradient descent is you step along the gradient of the smooth part, and then you apply this prox function to it. And the prox function is basically this thing. So there is an intuition for this based on, so if you remember way back here, we were approximating with a quadratic based on the derivative. So basically what we're doing in generalized gradient descent is we're using a quadratic approximation of the differentiable part, and then we're just adding on this convex non-differentiable part. So, okay. So far, in addition to talking about, until just now, we were talking about only methods that work for differentiable objective functions. We were also talking about optimizing these objective functions over all of Rn. They're unconstrained. Sometimes, though, we want to be able to optimize over a convex set. So say we want to find the minimum of some convex function over this convex set. That's not a convex set, sorry. Now it is. And so the way we can do that in this formalism is we can say, okay, g of x is whatever our objective, our convex objective, hopefully differentiable function is. H of x is what's usually called in optimization the indicator function. It's a little different than the indicator functions that people sometimes use. So it's whether, so let's call this set C. So it's a function that takes value infinity if x isn't in C, and 0 if it is. So what we just did was we replaced minimize over x in C f of x with minimize over x in Rn f of x plus an indicator function that x is in C. So if we're not in C, then this thing that we're optimizing will be infinity. So of course that's not going to be the minimum. And so the solution to these two problems is the same. Does that make sense to everyone? Okay. So the prox function for this indicator thing is this, right? Which, using the exact same argument we just did, is the same thing as the closest point in C to the closest point in C to this function x. So in this case, our generalized gradient descent that we get out is take a step along the gradient and then project what we get out of that step into our set that we're optimizing over. So that's also called projected gradient descent. So that's very useful, a very useful way to optimize functions over some convex set rather than over all of Rn. And it's important that the set we're optimizing over is convex. Otherwise, this indicator function wouldn't be convex. OK. Gradient descent is nice, but it's not always super fast. So we can do something called accelerated gradients, which basically, don't worry about the actual form of it here, this multiplier. But basically what we do is this is the normal gradient descent step if our old state was y, right? We just take x, that. It's the same thing as that. But instead of the old x, we're going to be using this thing y, which is equal to kind of a medium between the old step and the step before that. So we're keeping track of not only where we just were and taking a step from the gradient, but we're actually taking a step from, we're accounting for how much we took in the last step also. So this is a little unintuitive, and particularly this k minus 2 over k plus 1, where k is the number of the step you're on. That the reason why it has to be that, it comes out of the convergence proof. I don't know of an intuitive reason why that particular value makes sense as opposed to -3, but this is the one to use. So you may have heard of an algorithm called FISTA for solving the lasso problem, maybe. So that's what this is. It's an instance of this for lasso. So the nice thing about this, it seems like basically the same thing. It's almost no more work. But the nice thing is that the convergence rate is better than regular gradient descent. It's actually, you can prove it to be up to a big O, the best possible convergence rate for a first order method. A first order method is one that only uses the gradient. So that's pretty cool. One thing about it, though, is that it's not a descent method like SGD. So here's an example, small. Sorry, the picture's small. Here, does this zooming in thing work? No. Okay. So you can kind of see it. This is an actual example of, I think it's solving lasso. So gradient descent is this blue line here, where it's going down smoothly. It never increases, but it's not going down very fast, compared to the accelerated gradient method, which goes down way faster, but sometimes it jumps up. So these things are sometimes called Nesterov ripples, because Nesterov is the guy who came up with this accelerated gradient method. So a lot of times, the accelerated gradient will be substantially faster in practice than regular gradient descent, and it's almost no more work. So it's worth trying. Okay. So that was first order methods. There are some other variations you can make on it, but I just claimed, and there is a proof, if you want to see the proof, take 725, that this form of acceleration is the best you can possibly do up to constant factors for a first order method. So we can go beyond first order methods by accounting for the second derivative. So gradient descent, as we saw earlier, minimizes this thing. So you take the function, and then a linear approximation to the function, and then a second order term where you basically, it's a second order term of a fixed quadratic. What you do in Newton's method instead is you do the actual second order Taylor expansion. So you put in the Hessian there. And this is the second order Taylor expansion of f around your current point, and you minimize that. So the nice thing about Newton's method is that it's really super crazy fast in terms of number of iterations. Within a lot of times, gradient descent or even accelerated gradient descent will take hundreds, thousands of iterations to converge on a problem, and Newton's method will do it in 10 to more significant figures. The problem is those iterations cost a lot more than the first order method iterations, because computing the Hessian, if you can do it in closed form, it's not too bad, but in high dimensions, the matrix itself will be pretty big. And if you're doing, if you didn't compute the gradient in closed form, if you did something like, okay, so I didn't mention this earlier, but sometimes if you have a really complicated objective function, you can do, and you basically don't want to write out what it looks like as the whole, you don't want to take the derivative by hand, and you don't want to type it into Mathematica. You can do something called automatic differentiation, which basically says, if I'm taking my, I don't want to draw a picture of it. It's hard to draw a picture of. So, but basically what automatic differentiation does is as you're computing the actual function, in addition to the actual number of the function that comes out, it keeps track of the gradient of all the operations you applied, and it uses the chain rule to combine them all together to get the gradient locally to where you evaluated the function. So that's nice in that you don't have to work out the gradient analytically, and there are various software packages that do this for you. They do make evaluating the function slower because hardware knows how to multiply real numbers. It doesn't know how to keep track of gradients, so it slows down all your multiplications and stuff. But it can help a lot that you can't always even symbolically differentiate something if you just like wrote a function to do it. It's really hard to, but the software can do it. Okay, so anyway, if you're doing automatic differentiation, getting the Hessian can be pretty expensive. If you know it analytically, it's still a big matrix. If your dimensionality is p, then in first order methods like gradient descent, you only ever use your current iterate, which is a p-dimensional vector, maybe the last iterate before that, which is another p-dimensional vector, and then the gradient, which is also p-dimensional. But if you're using Newton's method, you have to keep track of a p by p matrix here, and to minimize this function, you have to invert it. So inverting matrix or solving linear systems of a p by p matrix is about p cubed, which gets really expensive really fast. So you can't really afford Newton's method in high dimensions. Also, Newton's method has a bad tendency to, if you start in a bad place, even with a nice function, it might diverge. So you have to kind of keep track of that. So one thing you can do is actually do kind of a backtracking-like thing, which is the line search thing here. Or you can also do something called the trust region, which is basically you take the Hessian and you add a little bit of you add some to the identity. So that basically adds a quadratic like you had for gradient descent onto it. So if your true, well, it's convex, so that can't happen. If your true quadratic second derivative looks like that, it basically makes it a little tighter. Doesn't trust it as much. That's why it's called the trust region. So those are various things that can help with avoiding divergence of Newton's method. So to avoid the computational expense, there are various things you can do called quasi-Newton methods, which help, they basically approximate the Hessian rather than actually computing the full thing. So that can be a lot less expensive. So there's this algorithm proposed in the 70s by guys whose initials were BF, G, and S. So there's this algorithm BFGS that's pretty good that it basically takes, based on the gradient evaluations you have, it keeps an estimate, a low rank estimate of the Hessian as you go without actually ever computing it. And then LBFGS is similar, but uses more limited memory. So that's kind of the standard quasi-Newton method that you'll find, I'm sure, so MATLAB uses that, SciPy has a function for it, R has a function for it. That's kind of the standard, I have this function and I want to optimize it with a quasi-Newton method, that's what you go to first. But don't ever write it yourself, it's terrible. And you can also do something called truncated Newton, which basically, instead of inverting this Hessian matrix, it only partially gets the answer. So it uses something called conjugate gradient, which is basically, it's a cheaper way to approximately solve the solution here. And so depending on exactly what you do with it, that can make some pretty nice quasi-Newton methods also. Okay. So that's an overview of, I have an arbitrary function and I want to optimize it. Do you have any questions about what we've talked about so far? Okay. So another nice thing when you're optimizing is that people have been studying optimization for a long time. And there are certain problem setups that you can do that people have spent careers trying to solve them as fast as possible. And there are people at CMU who do that. So basically, the most famous one is linear programs. So that's when your objective function is linear and you have various linear constraints on your variables. And if that's true, there's all kinds of fancy algorithms that'll solve these pretty quickly, very accurately. You can also generalize that a little bit to quadratic programs, where you add a quadratic term to the objective and you still only have linear constraints on it. So this is a convex problem only if H is PSD. If H isn't PSD, then this problem is actually NP-hard, because you can write So you can write any SAT problem as a quadratic problem, except that your H matrix ends up being not PSD. But if it is PSD and the problem's convex, then you can solve it pretty well, pretty quickly. A generalization of that is cone programs, which are a linear objective when your constraints are that you have various constraints that things lie in an arbitrary convex cone. So we talked about convex cones a little bit in class. That's basically just that they're closed under positive scalar multiplication and are also convex sets. So that's a pretty general form of optimization. So if you're looking at if you say, okay, I have this thing I want to optimize, how can I optimize it? If it turns out that there's a way you can kind of rewrite your problem as an LP, as a QP, as an STP, as any of these other various standard forms of optimization problems, then you can just basically make these constraint matrices, figure out how to write it that way, and plug it into some solver that's out there, and it'll be much better than if you just wrote some little code to solve your problem. If this is a problem that your startup success depends on getting this solved as fast as possible, you might be able to do it better by tailoring your solver to that particular problem, but that'll probably cost you months of your life and may not help that much. So if you can write your optimization, if you can write your objective and your problem in one of these forms, just do it and you'll get a good answer quick. Okay, so that's all the slides I had on convex optimization. In addition to convex optimization, if it turns out that you really need to optimize a non-convex problem, there are different things you can do. They're kind of beyond the scope of this class or this recitation. Alex talked a little bit in lecture about integer programs, which are basically where some of your variables are constrained to be integers, which makes everything harder because you can't do gradient descent or anything like it on integers because you can only be 0 or 1 or 2 or whatever. So that makes life a lot harder. Combinatorial optimization is definitely harder than convex optimization. But sometimes you need to do it. And so there are kind of standard problem forms like integer programs for this. And there are like mixed integer linear programs, and there are all kinds of things like that, that if you have to solve a problem like that, you can go to Wikipedia and look at the mathematical optimization page, see which problem form your problem fits into, and try to get that to work. If you are optimizing a continuous function, or a like real valued function that the domain is the reals, sorry. If you have some optimization problem that is not convex but is in Rn, then there are different things you can do to try to solve it. You can try to do a convex relaxation, which is find a convex problem that's similar to your problem, optimize that, and then, so a relaxation actually is a more general thing. That's also kind of beyond the scope of what we're talking about now, but you can do things like try to find a convex problem that's similar and then solve that and update your answer based to actually solve the real problem you're trying to solve. You can also do various kinds of bounds. We'll talk later in the class about expectation maximization, which is an algorithm for optimizing a particular kind of non-convex objective function, but we'll definitely talk about that in a few weeks sometime. So that's most of what I wanted to talk about. I also wanted to go through quickly an example of a practical problem that someone posted on Stack Exchange. I think it's big enough to see. So this is, someone posted on here. I have this statistics problem. I want to solve it. How can I do it? I don't know how to do it. So I'm not going to, we're not going to read the whole thing. But so basically his statistics problem was he can observe the differences between a lot of random variables. So he has a sequence of random variables that add up to 0. And he has a lot of observations of the differences between different pairs of them. But he doesn't have any observations of the variables himself. And so based on the differences between them, he wants to get an estimate of the actual values of the random variables. So what you can do then is you can actually convert this. So if you make a certain assumption, so you assume that the noise, your observations have random noise, IID random noise, then you can write down a likelihood function for this that for a particular sequence, you set the probability density is then 0 if it doesn't add to 0, and then the product of a bunch of normals. So the normal of your observation around the difference between the two with some variance that you don't know. And then you can maximize that. So this function is not convex, this likelihood. But the log likelihood, well, so here's the likelihood written a slightly different way. So combining all the exponentials together, subject to this constraint that they all add up to 0. You take the log, you get out this. So what I did here is basically you can simplify this maximization problem because if you're maximizing the square root of a function and you maximize the function itself where the value is non-negative, it's the same thing. So you can square that and your answer will still be the same. Obviously the value, the maximum you get out will be different, but the value s that maximizes it will be the same. So you can square that, you can get rid of that constant in the front that divide by square root of 2 pi sigma, and then you can take so you get that exponential. You can then take the log of that, because log also, if you maximize the function, maximize the log, same thing, assuming it's positive. And then get rid of that other scaling factor. You end up with just minimizing this fairly simple sum of squares. So continuing to do some expansion, you can expand out those squares, get a bunch of things, use some facts about what the variables actually mean. The details don't matter here. But the point is, eventually, you can write it down as a quadratic program. And then, well, here, now it's a quadratic program. We can divide by 2. So then, because it's a quadratic program, you know the solution, or you can plug it into a solution. In this case, because there's only one equality constraint, you can actually just write it down as the solution to this matrix equation. And because of various things we know about it, whatever, blah blah blah, you can talk about that it's convex, that it has a unique maximizer, etc. So I just thought that was a cool example of. I didn't talk about it in enough detail for it to be really cool, but it's a neat example of if you think about if you know the standard forms of problems, you can try to manipulate things that don't seem like they should be a quadratic program into a quadratic program, and then they're easy to solve. Yeah, I probably should have come up with a simpler example that I could actually explain the details on for that, but didn't, sorry. Okay, so that's all the material I wanted to talk about. Does anyone have any questions about what we talked about today? Homework 2, homework 1, anything? Nope? Okay, cool.